Today I'll be doing LeetCode Weekly Contest 180, and I'll be explaining my solutions after I solve all the problems. So I'll just check each element. So minimum in row. And maximum in column. But looking at the sample cases, I don't know if the answer is always just one element. So basically just lazy add operations. At most 1,000 calls, we add the constraints that low. Teapot. Okay, well, think first I need to find the nodes in the array. So like in order traversal. Okay, this looks good. Accepted, okay. Then we just return nothing, but otherwise. Two, 1, 3. No, 4. Okay, this seems to work. Supplied by the minimum efficiency. Accepted. Okay, cool. I think we need to sort efficiency first. Oh yeah, okay, we just sort. At most K engineers. Put the speed, and then if it's greater than K, then I have to remove. also maintain the sum. Then I update the answer. $60, $68, $72. Okay, I can submit this. This is probably going to be correct. So, okay, accepted. I think this is one of my best performances. Oh, third place. That's not bad. Cool, okay. So I'll start with the explanations. Wait, actually, I don't know. I don't know if the answer will always be just one element. I need to test to see if the answer will always be just one element. Wait, it seems like the answer is always going to be one element, but I don't know why. Or maybe not. Wait. So I have okay, then it's just empty. So can there be more than one? I think if I think there can be at most one element, because if this is the minimum of this row and then this is also the maximum of this column, then that means that the other minimums in these rows will have to be less than the minimum in this row, which means that these can't be the maximum of the column. So there's at most one element in the answer, okay? Okay, I'll actually start with the explanations now. So for the first problem, you can just loop through each element. You try each cell in the matrix, and then for each cell in the matrix, you compute the minimum in that row, and you compute the maximum in that column. And then if the minimum and the maximum is both equal to the cell, so if it satisfies this condition, then you just add it to the answer, and you return the answer. For the second problem, I'm not sure if it seems like O of n squared, a quadratic time solution will pass for this, but I used the linear time solution. So basically, I used the idea of prefix sums to add to perform this operation in constant time. So what I do is, instead of adding to all of the last k elements, I just add to a lazy value for the kth element in the stack, and then whenever I pop the element from the stack, I add the lazy value onto the previous element. So then the value that I add to the first k elements, they will be added to the elements when I perform the pop operation. So it's kind of like prefix sums. And then most of the other operations are pretty much straightforward. So for push, so I stored the size of the stack in this variable s. So if the size of the stack is already exceeded the max size, then I just don't do anything. And otherwise I set the next element of the stack equal to x, and then initially the lazy add value for the new element is 0. And then when I pop, if there's no elements, I just return -1. And otherwise, I return the element of the stack plus the lazy add value. And then if there are more elements after this element, then I add the lazy add value to the next element. And then I decrease the size by 1, and then I return the value of the element. And for increment, as I said earlier, if there are no elements in the stack, then I don't do anything. But otherwise, I take the minimum of k and s to find out exactly how many elements I add to, and then I only add to the last element of those k elements. Yeah, okay. So for the third problem, this is actually I think this is a pretty standard problem. So in order to make the binary search tree balanced, what we want to do is, so you know how in like merge sort or quick sort, you basically want to partition the array into equal halves. So then the depth of the entire recursive function will be as small as possible. And this is what I do here. So the first thing I do is, since we need the same node values, in my first DFS, I retrieve the node values and I get them in sorted order by finding the in-order traversal of the binary search tree. Because the in-order traversal of a binary search tree always gives you the values in sorted order. Then after sorting A, I basically perform a recursive function which works kind of like merge sort. So I take the middle of the current range, and then I set the root of this range equal to the element in the middle. And then I find the root for the left subtree and for the right subtree from the ranges L to m-1 and m+1 to r. And lastly, I just return this root. And then for the answer, it's just the root for the range of the entire array of the values. So for this problem, one idea we should try is to sort the efficiency of the engineers. Basically, if we'll iterate over the minimum efficiency of the engineers. So I'll sort this, I'll sort the engineers first. So this is speed, this is efficiency. Then we have and then in my solution, I fixed the minimum efficiency of the engineers. So basically say that, let's suppose that the minimum efficiency has to be greater than or equal to this. Then what will the answer be? And then let's suppose that the minimum efficiency has to be greater than or equal to 7. Then what will the efficiency be? And so on. So how we actually check for each value in the efficiency is basically just take all the engineers with a value greater than or equal to the current the current efficiency we're checking for. In this example, k equals to 2. So then what we do is we just choose the two biggest elements, and then we add them up. So then the performance for a minimum efficiency of 5 will be equal to 35. And then we try, for example, this one. We have a minimum efficiency of 4, and the best two elements have speeds 10 and 5. So the performance with a minimum efficiency of 4 is 60. And yeah, so in order to do, the constraints are up to 10 to the 5. So we need to do this efficiently. And the way we do that is we start with the minimum efficiency from the back, and then as we process all of the engineers, we will add their speeds into a priority queue. And then in the priority queue, I'll only maintain the k top elements. I'll maintain the sum of the k top elements in order to find the performance, the maximum performance. So in my code here, first thing I do is I sort the engineers by their efficiency first, and then by their speed. It actually doesn't matter how you tie break the engineers if they have the same efficiency. And in my answer here, I store the maximum answer I've encountered so far, and as stores the sum of the top k engineers, we have the sum of the speeds of the best k engineers we have found so far. And this priority queue stores the set of those speeds. So when we process a new engineer, we add its speed to the priority queue, and then we also update the sum. And then if the priority queue has more than k engineers, then the priority queue will give us the smallest element in the set. So we subtract that from our sum and then we remove it from the priority queue. And then finally, we update the answer with the sum of the speeds multiplied by the minimum efficiency. And we return the answer modulo m. And this is basically it for the solutions. So if you think that this video was helpful, then feel free to like and subscribe. And if you have any questions, feel free to ask them in the comments below so I can help you and so that I can also improve my explanations.